Hello everybody. Today we will do 4.2 exponential functions, and you will see 4.3 natural exponential functions is closely related to this 4.2. I may just consider, you can see that that's continuation from 4.2, and then after we're done with 4.2, 4.3, we will go on with 4.4. As I remember, that's where our test 2 will end, and your test 2 will be this Friday. Okay, let's start with basic exponential function. So basic exponential function has the following pattern. Y equals to, let me see what notation our test will use, A or B for the base. Yeah, our textbook use A for the base. I usually use B for the base. Okay, Y equals to A to the X. No coefficient at the front, no plus minus, no variation on the top there. Just something to the X, a number to the X, that's it. Okay, where the A is greater than 0 and A is not equals to 1. For example, the one that we will be dealing with very soon is Y equals to 2 to the X. We can also write it as Fx equals to 2 to the X. Okay, the one that you need to keep in mind is that the A there, the A, if you look at the number line, the A has to be greater than 0, cannot be 0, okay, and cannot be 1. Okay, is between 0, not including 0, to infinity. The base can be anything, but we will skip 1. Okay, I will explain later on why we don't have the negative, why we don't have the 0, why don't we have the 1. But for now, we take it that the basic exponential function will have the base, positive base. It has to be positive, but cannot be 0. Okay, now our focus will be on the graph. We'll learn to graph that, and then hopefully from the graph we can see the domain, the range, and so on and so forth. I can just show you using my graphing software to show you what the graph look like, but we won't see the detail by doing so. Now, instead, let's do the following. Let's do the table. So let's create a table. So again, let's continue here. Example 1, let me call that example 1. Let fx equals to 2 to the x. Okay, now our main purpose is to graph it and see how's the behavior, x-intercept, y-intercept, and so on. But for that to happen, let's get some feeling about this. Okay, we will get, we start with 0 then. When x equals to 0, the y will be 2 to the 0, which is 1. X is 1, the y will be 2 to the 1, which is 2. And x is 2, that would be 2 squared, that's 4. If I do some little insert, let me set that here. Huh? Maybe that's not okay. I want to insert here. Oh, that's not work. Okay. Let's see. So if x equals to 0, that's 2 to the 0. Let me step back by 1 unit. So x to the when x is -1, there will be 2 to the -1, which is 1/2. And when x is -2, there will be 2 to the power of -2, which is 1/4. Now, if we sketch the these coordinates here, if we connect these coordinates here, then when x equals to 0, I get 0, 1, right? This is 0, 1. The coordinate x, y. Okay, and then when x equals to 1, the y is 2. I try to make it as well scaled as possible. And then 2, 4, 2, 4 is here. While when x equals to -1, the y is 1/2. -1, 1/2, -2, 1/4. If I connect these coordinates here, you will see the following graph. Oops, that's not nice. Actually, you will see that it will never touch the x-axis. Okay, it will never touch the x-axis. And I will explain it right now why we know it will not touch the x-axis. Notice that when x equals to 0, the y-intercept is 1, right? When we move 1 unit to the right, then whatever the value we have before, when we move 1 unit to the right, we double it because the base is 2. So when we move 1 unit to the right, it's not like linear function. Linear function, every time you move to the right, you add or subtract by a constant, right? Okay, by a certain number, which we call the slope. Right now, you actually multiply. Okay, you actually multiply because the base is 2. Then every time you go to the right, you multiply by 2. When I go to the right 1 more unit, then whatever the previous result, 2 now becomes 4. Okay, so you will see if the base is 2, then every 1 unit you move to the right, you will multiply the previous result by 2, multiply the previous result by 2. Okay, so you can tell when x equals to 3, the y will be multiply that 4 by 2, give you 8. Again, because the base is 2, so I keep on multiplying by 2. I hope you see that. Okay, I hope you see that. Now, using the same logic, then, what happens if we go to the left? If we go to the left, instead of multiply by 2, we will divide by 2. Instead of multiplying by 2, we will divide by 2. So you see that from 0, when I go to the left 1 unit, I will divide by 2. Well, because when you come from here, go to the right, you multiply by 2. Okay, so when you go to the left, you divide by 2, divide by 2, divide by 2, divide by 2, and on. So notice that any positive number, however small it is, when you divide by 2, there will still be a positive number. Okay, so imagine if you pick a positive number somewhere on the left hand side here. It's already a small positive number. You already have a small positive number. When you go 1 unit to the left, you divide by 2. You divide by 2, divide by 2, divide by 2. Now, however many times you do that, the value will still be positive, even though it gets smaller, but it will never be 0. Okay, that's how we know that this graph here will get very close to x-axis, but never touch. Okay, but the right hand side, we know because it keep on multiplying by 2, then this will explode eventually goes to infinity. Okay. Now you will see that we have the same behavior even if I change that 2 becomes 3, becomes 4, or any number more than 1. If the base is, let's say, if I have y equals to 1.7x, right? Then every time we move 1 unit to the right, I will multiply the previous result by 1.7. Right? So it will be increasing, right? It will be increasing. So what can we see from here? It means as x goes to negative infinity, the fx, the basic exponential function, is going to 0. That's the limit. But it will not touch, but gets closer. As x goes to positive infinity, the function, the value of the function will go to infinity as well. Now that is for the base greater than 1, because you keep on multiplying by something more than 1. So if the more you go to the right, the greater the number is. Okay. We also see that the y-intercept is always 0, 1. Okay. The domain clearly is all real numbers. Okay. But from the graph, you see the range will not be negative. In fact, cannot even be 0. The range will be from 0 to infinity. Cannot touch 0, right? Never touch 0. Remember I said it here, never touch 0. Never touch x-axis. Now, because the range does not include 0, then to our understanding, for sure that then there will be no x-intercept also. Because x-intercept requires the y to be 0, but according to our range and according to our graph, there we never get the y equals 0. Okay? Never get the y equals 0. Because the base is greater than 1, you will see that it will be increasing. Okay, the graph will be increasing. Now, let's take a look on our graphing software to do some comparison. You will see that as long as the base is greater than 1, then the function is increasing. So you see here we have the graph of 2 to the x. Okay, now let's compare that with other basic exponential functions. Let me use y equals to 3 to the x. So 3 to the x means every 1 unit to the right, you will multiply the previous value by 3. Okay, then you will see it goes to infinity a lot faster, but at the same time, when you go to the left, you divide by 3. So it dies down to 0 a lot faster. Now, from the color, I believe you can see the distinction between which is 2 to the x, which is 3 to the x, right? Okay, you see that for 3 to the x, it goes to infinity faster, the red one. 3 to the x goes to infinity faster, but at the same time, it dies down faster. Okay, now if I exaggerate that, let's say I exaggerate that to 10 to the x, y equals to 10 to the x. Now you see that 10 to the x, the blue one actually explodes to infinity a lot faster, but at the same time goes down a lot faster. Now the thing is, even if I make it instead 1.7, okay, it's greater than 1, right? So it will still be increasing. You see the blue one right now? It's still increasing, but it increases slower. And at the same time, it decreases slower. Okay, let me picture this. just for comparison, together with the color. You can see here that that the red one, it will go definitely farther. So this is 3 to the x. The purple one, do I have purple color? Do I have a purple color? This one. Okay, the purple color 2 to the x. And the blue color is 1.7 to the x. Okay, so you see important things that in any case, the y-intercept is 0, 1, and in any case, no x-intercept. In any base, the domain is all real number. The range is from 0 to infinity. When I say for any base here, you will see it also includes when the base is between 0 to 1. Okay, and then the y-intercept is always 0, 1, that coordinate. Okay, the x-intercept is none. And we have horizontal asymptote. Horizontal, I think I want to say one-sided. Horizontal asymptote is y equals to 0. That's for any base. Then going further, for a greater than 1, then the graph is increasing. Okay, so the far end behavior will be approaching 0. When you go to the left, it's approaching 0. When you go to the right, it will be. Okay, while when the base is between 0 to 1, I will graph for you later on very soon. You will see that the graph will be decreasing with far end behavior. To the left hand side, it goes to infinity. To the right hand side, it goes to 0. Okay, but one important key is that in either case, the base is greater than 1 or between 0 to 1, it's strictly increasing or strictly decreasing, and therefore, in any case, the function, basic exponential function, will then be 1 to 1. Now, that's an important ingredient we will need later on in 4.4. Okay, now that is also an ingredient we need when we solve some simple exponential function later, simple exponential equation later on. Okay, now let's see some more graph. Let me go back to my graphing. This time, let's use the base to be, let's say, 0.5 and 0.3. 0.3 and then 0.7. By doing so, we would be able to actually observe some important ingredients from here. You see from this graph that when the base is between 0 to 1, as long as the base between 0 to 1, then the graph will be decreasing. Okay, the blue one is, this is 0.7 to the x. The purple one, where's my purple color? Purple color is 0.5 to the x. Of course, it goes indefinitely far. And then my red one, this is 0.3 to the x. Okay. You can also see the following. I give you a little example, like that's 0.5x, for example. 0.5x, for example. That's 1/2 to the x, right? That's 1/2 to the x, which we can see 2 to the negative x. So in some sense, we can see this. We can see the graph of the graph of 1/2 to the x as the reflection with respect to y-axis of y from y equals to 2 to the x graph. Okay, so y equals to 2 to the x is something like this, right? That's 2 to the x. Now replacing x by negative x, replacing x by negative x, replacing x by negative x, that's the reflection with respect to y-axis. We learned that, I think, at the beginning of chapter 3, or somewhere in chapter 1. I don't remember precisely. I think it's chapter 2. I'm sorry, chapter 2. Chapter 2.2, 2.3, somewhere there. Okay, so when you reflect that with respect to the y-axis, then it looks like this. Okay. Now, that's, I think, a very good note that helps us to see, oh, you know what? So 0 point something to the x, that's basically reflection of some integer greater than 1 to the x with respect to y-axis. Okay, now, hopefully then it helps us to see what are the far-end behavior. Okay, now, but from here, I want you to notice the behavior around near y-axis, and that will be part that I call important coordinates. When you graph an exponential function, you need to include these important coordinates. What are those? The ones coming from the y-intercept, and this guy here, and this guy here. These are the three important coordinates. Okay, when y equals, not because y equals to 0. It's more about that in the basic exponential function, the three important coordinates are these 3 points here. Okay, so 0, 1 is the y-intercept, that's one of them. When you move one unit to the right, multiply by the 1 by whatever the base. In this case, that's base 2, so I multiply by 2. And when I go to the left, I divide by 2. Okay, let's use the example, the red one here, the red color, 3 to the x. So the important coordinates will be 0, 1, 1, 3, and negative 1, 1/3. Okay, now if you graph this without graphing paper, like so when in your test or in your quiz, you happen to use not using graphing paper, then I require you to actually put a dot there and write down the coordinate 1, 3. Okay, and this one is negative 1/3. Yeah. Okay, suppose we look at this one here. The red one, again, the important coordinates are 0, 1, and this guy here will be 1, comma, the reciprocal of 0.3. That's 10/3. Okay, and then I'm sorry. what am I doing? That's the one when x equals to negative. So this is 1, 0.3 here, while this one here, that will be -1, 10/3. Or you can make it decimal if you like. Okay, so this coordinate, that coordinate. Those are the three important coordinates. Now, why I say that these three coordinates are important coordinates, let me use this example 2 to the x. That's because the bend, how the curve actually bending, is actually most important at these 3 points. The bend, so you will see that the one happens after that, this section here, it's not bending as much. Like the one here is not bending as much, and also the bend is actually a lot happening here. Okay, so imagine if you drive along a curve. When you drive along the curve that looks like this, then you don't really feel any centripetal or centrifugal force when you are in this blue region. Likewise, if you are in this blue region, you don't feel that much force that push you to the right. Okay, but during this region here, when you are in this section, that's when you feel the most. Okay, so if you don't feel anything here, then you won't feel anything here. Okay, when imagine if you are driving in your car, right, and then you go through the curve like that, then the force will be uh, the push, or yeah, the push toward to right hand side. If you drive from left to right here, then the push that make you tilt to the right is actually the most happening here. Okay, so imagine if you need to design a freeway later on, and the entrance or the exit of the freeway happens to mimic this exponential function, then the way they know what is your maximum speed when you turn is by looking at the place where it bends the most and see what is the safe speed to pass that bend. Okay. Now that's why I require you to give me those three important coordinates. There. Let me erase the coloring. Okay. Now from this explanation, let's summarize it. Use a big red color. Summary. Summary. Let y equals to a to dx, where the a is positive and a cannot be 1. Okay. Then first, the domain is all real number. You can plug in any x and it will give you a real number. But the range, whatever x you plug in, the outcome will never be 0, will never be negative. It's always positive. The y-intercept is 0, 1. In fact, let me say more. And two other important coordinates are 1, a. So imagine if you move 1 unit to the right. If you move 1 unit to the right, then you will multiply the 1 by the base a. Okay, now the other important coordinates when the x is -1. When x is -1, you move 1 unit to the left, such that the y now becomes 1/a. Okay, now when I say three important coordinates refers to the coordinates associated to this. Okay, those are what I call three important coordinates. Every time you graph exponential function, regardless it's base or exponent, it must includes the transformation from these three coordinates. Now, I will explain that very soon later. Okay, part B. Part D, x-intercept, non, horizontal asymptote, y equals 0. In fact, we can say that when the a is greater than 1, then as x goes to infinity, if you go to the far right, the y will go to infinity. As x goes to negative infinity, the y gets closer to 0, but never touch. Now, if the a is between 0 and 1, then when x goes to positive infinity, y goes to 0. Imagine you reflect this case here. Imagine if you reflect this case here, becomes with respect to the y-axis. Okay, then you will get something on the left. So as x goes to negative infinity, the y will go to infinity. Okay, so either way, the function is 1 to 1. Either it is strictly increasing or strictly decreasing. Either way, it is 1 to 1. Now, that's the property that I would like to use now to solve some basic equation, to solve some basic exponential equation. One-to-oneness, to solve one-to-oneness, to solve basic exponential function, exponential equation. For example, let me pick question number 2. Question number 2 in our textbook. We need to solve 6 to the 7 minus x equals to 6 to the 2x plus 1. Now, the idea is a to the blah equals to a to the blah implies, if they have the same base, implies the blah equals to blah. Okay, that's the idea of one-to-oneness. So 6 to blah equals to 6 to blah implies the exponent has to be the same. Okay, so I will get 6 equals to 3x, x equals to 2. But you may wonder, what does it have to do? What does it has to do? Has to do with one-to-one. This is where the one-to-oneness happens. That's where we use it. That's where we use it. Notice that the phenomena is not always doable. Let's say if I have 2 to the power of 4 equals to x to the power of 4. Now, it does not consequently implies x equals to 2. No. In fact, the answer is x can be 2 or x can be negative 2. Okay? Now, one-to-oneness means if you have a solution, that's the solution. That's one-to-oneness. If you can find a solution, that is the solution. But without one-to-oneness, if that function is not one-to-one, like in this case, in my counter example here, x to the 4th, this is not a one-to-one function. This is not one-to-one, not one-to-one. If you graph that, it looks like a skinnier parabola. Okay, it looks like a skinnier parabola. So when y equals to 16, that's 2 to the 4th, right? When y equals to 16, there are two possible x that gives you that 16, negative 2 and positive 2. Okay? Now, for exponential function, from the graph, we know it's one-to-one, such that if you have 6 to the blah equals to 6 to the blah should equals to blah. Okay, now with that said, then to solve basic exponential function, one basic technique is to change the base into the same base, such that we can just operate or work on the exponent. Number 8, for example. Number 8, 27 to the power of x minus 1 equals to 9 to the power of 2x minus 3. Now, 27 and 9 are both a number of base 3. 27 is 3 cubed. 9 is 3 squared. Okay, simplify the left-hand side. And the right-hand side, 3 to the 4x 6. Now then, from here, by one-to-oneness, we get the exponent on the left-hand side equals to the exponent on the right-hand side. Again, without one-to-oneness, this is not doable. Okay, you see the example on the right-hand side, right? Okay, just imagine when another example, when x squared equals to 3 squared. Dare you not say x equals to 3 only? No, that's not true. In fact, the proper way to solve that is x squared equals to 9, and then we apply square root property. Don't forget the plus minus. So x is plus minus 3. There are two solutions there. Okay? And from here, if I solve that, negative 3 plus 6 equals to 4x minus 3x. So 3 equals to x. Okay. Now that's for number 2, the one-to-oneness and how to solve simple exponential equations. Now, how about exponential function in general? Exponential function in general. I think I want to insert the word more general, but not super general. We will be dealing with this kind of function. Fx equals to, let's say, 2 to the x plus 3 minus 4. For example, 2 to the x plus 3 minus 4. Then how do we graph this? Now we know the domain of 2 to the x. The domain of 2 to the x is all real number, such that however you move it, the domain will still be all real number. Okay, now, but how about the range? The range for 2 to the x, the range, maybe we, instead of looking at the range only, let's take a look on what the graph should look like. Okay, 2 to the x, as we have done earlier, it's an increasing function. And then the y-intercept is here. Okay, then what happens if I have 2 to the x plus 3. Then we will move 3 units to the left. So the y-intercept now kind of like moving here. Okay, so the graph is now like this. Okay, that's what the graph looks like, and this is where the original y-intercept now move here. So this coordinate is now negative 3, 1. Now, then from there we move down 4 units. So we move down 4 units. The horizontal asymptote originally at y equals to 0. Now the horizontal asymptote becomes y equals to 4. Okay, and this negative 3, 1. When I move 4 units down, it becomes negative 3, negative 3. Yeah, imagine if you move the y equals to 1 down 4 units. So it will be here. Okay, but then remember that we have 3 important coordinates, right? This is one of them. Now the other one will be here, and the other one will be here. So the graph will look like this later on, approximately. We can find the x-intercept and the y-intercept later on by computation, okay? But by sketch, that's what the graph looks like. So from there, we see that the range will be from negative 4, not including negative 4, to infinity. How about the y-intercept? The y-intercept, you plug in x equals to 0. That's 2 to the 0 plus 3 minus 4. That's 2 cubed minus 4. 8 minus 4, that's 4. So the y-intercept is 0, 4. Okay, so now we know this will be 0, 4. Okay, and then part D, how about the x-intercept? From the sketch of our graph, or even from the range, you see the range including 0. The range includes 0. It means there must be some x such that the y equals to 0. Right? At least by intermediate value theorem, remember? This exponential function is continuous everywhere. Okay, so if there's a y equals to a negative number and the y-intercept is positive number, then there must be a 0 in between. How to find that? We replace the fx by 0 and solve for x. 4 equals to 2 to the x plus 3. Let me rewrite that 4 as 2 squared. I make the same base such that x plus 3 equals to 2, x equals to negative 1. So my x-intercept is negative 1, 0. Part E, horizontal asymptote is y equals to negative 4. Okay, in fact, we can go further. As x goes to infinity, when we go very far to the right, fx will go to infinity. Not equal, but will go to. And as x goes to negative infinity, and the function will approaches negative 4. Okay, so this is a one-sided horizontal asymptote. Now, how about the graph? I will try to graph that now, but I need to graph in paper. Give me a second. This in paper. I didn't know. Okay. Oh, what happened? Something not right with my software. Something not right with my software. I wonder what happened. Let me sketch this graphing paper to help us. Let's say we have that graphing paper, okay? And then let's put the note on important coordinates. The y-intercept is 0, 4. X-intercept is -1, 0. Okay, the original graph 2 to the x has 0, 1, 1, 2, -1, 1/2. Okay, I use this gray coordinates here. Okay, now then do that movement. Move 3 units to the left. So this guy here, move 3 units to the left and 4 units down. So the new coordinate for that gray one now here. Okay, the y-intercept, the y-intercept originally 0, 1, move 3 units to the left, move 3 units to the left, 1, 2, 3, and 4 units down, 1, 2, 3, 4. So the y-intercept now move here. Okay, now how about the third important coordinates? The third important coordinates, this guy, -1, 1/2. Move 3 units to the left, 4 units down, 1, 2, 3, 4, in between there. So this is the third important coordinate. So you see that these 3 important coordinates for 2 to the x now move here. Okay, let's now move there. And that helps us to plot the coordinates even better later on. Let me just erase this now. Okay, or let me just leave them there. Let me just leave them there. Okay, and then horizontal asymptote. Horizontal asymptotes, we know that's y equals to -4. This is the horizontal asymptote. Okay, now if I connect the points for the graph, it will be in straight. It will be very close to horizontal asymptote. So start going up. Okay, that's what the graph looks like. That's what the graph looks like. Now let's do one more question before we take a break. What if we have number, textbook? I try to pick something not too harsh for us to graph. Let me do number 19. Number 19, that's an odd number. Usually I want you to do that. Number 19, fx equals to -1/2 to the x plus 4. -1/2 to the x plus 4. The sketch will be, let's start from 1/2 to the x first. 1/2 to the x. 1/2 to the x, we know will be something like this. Okay, now then what happens if I put negative in front of that? Then you put negative on the y, right? Basically, then what happens is you reflect that with respect to the x-axis. Okay, and then when you add 4 to the whole function, it means you move the graph up by 4 units. So the horizontal asymptote originally at y equals to 0, the x-axis. Now the horizontal asymptote will be y equals to 4. Okay, and it will look approximately like this. It will look approximately. Okay. Now, from that sketch of the graph, you may be able to do it in your, you may be able to do it mentally, but I strongly suggest you to at least do that sketch on your scratch paper. Okay, you don't need to show that to me though. Yeah, your scratch paper doesn't count, but if you put it on your test paper, then I have to grade it as part of your submission. Okay, the domain will be, as before, all real numbers. The range, now we see, it's from negative infinity up to 4, but not including 4. But the y-intercept? The y-intercept, take a look on F0. It will be negative 1/2 to the 0 plus 4. That's negative 1 plus 4. That's 3. Y-intercept is 0, 3. Okay, so if you do this one here, this coordinate here will be 0, 3. Okay, but how about the x-intercept? See, this is part A, part B, part C, part D. Oops, no, that's not. Part D is the x-intercept. Then I set the function to be 0 and solve for x. This is 1/2 to the x equals to 4. Now 1/2 is 2 to the negative 1. And 4 is 2 squared. So 2 to the negative x equals to 2 squared. It means negative x equals to 2. X is negative 2. So the x-intercept is negative 2, 0. Part E, horizontal asymptote, y equals to 4, as we have seen earlier. And if you want to go a bit more detailed, we say as x goes to infinity, from the graph you can see that the fx will approach 4. As x goes to negative infinity, the function will go to negative infinity. Okay, now let's sketch the graph. Put it here. Oops. Then the x-intercept is negative 2, 0. The y-intercept is 0, 3 as I remember. And then horizontal asymptote y equals to 4. Oops. This is the y-intercept. I mean, horizontal asymptote, y equals to 4. But then, how about those 3 important coordinates that we talked about? Originally, those 3 important coordinates were here, here, here. Right? That's 1/2 to the x. Now then, when I put negative in front of that 1/2 to the x, when I put negative in front of that 1/2 to the x, okay, I basically flip the graph upside down. So these 3 coordinates then becomes this guy here, and this guy here. Okay, not here anymore, but those 3. Let me make it bigger here, and here, and here. Now, move each one of them 4 units up. So you will see this guy here, when I move 4 units up, I get that one. This guy move 4 units up, give me this. This guy 4 units up, give me this. Okay. Now, of course, if you can put more coordinates, that would be great. For example, I know if I go 1 more to the left, that's negative 4, then it should be negative 8. So the graph will be something else like this. Imagine the bending. The bending happened the most at in between those three important coordinates. The bending happens the most here. Okay, that's why I need you to include that though. Again, if you don't have graphing paper, when I ask you to sketch this, you don't have graphing paper, then you need to plug in the coordinates. Okay, not just putting the points. This would be 1, 3.5. This is 0.3. This is -1.2. This is 2, -2.0. Okay, and this is -3, what am I doing? That's right. Okay, that's for the graph. I will not do most of the graph in your graph in the textbook. I will do more from this 4.2 later. I will do more graphing, but I will not do all of them in details. But some special cases can be done in a nice way. Okay, let's take a little break first. We take a break for 10 minutes. We come back at 12:19. Okay, let's continue. I will start working on not so basic, not so basic exponential function. At least not the one that we encountered earlier. Exponential function. So not the basic one, and not the one that we do transformation on. So x plus something, and then plus something like that. No, not these two. Okay, not these two. Not these two. Let's say, for example, we take a look on number 24. Number 24. Implicitly, by going over this problem, I also show you the technique on using all the material that we learned before. Fx equals to 2 to the power of negative absolute x. Now, first that we note that when we replace x by negative x, we get 2 to the power of negative absolute of negative x. Okay, but absolute of negative x is the same to absolute of x, right? Okay, and that gives us the original function. But because f negative x equals to fx, it means when we reflect with respect to the y-axis, it will match the original graph. Okay, when we reflect fx to the graph of with respect to y-axis, the result match fx itself. We say, therefore, the graph is has graph of fx has y-axis symmetry. The function itself is called even function. Okay, it has y-axis symmetry. Now, then it gives us a hint. So if we can graph the positive part, the positive side, I was referring to x greater or equals to 0, then reflecting it with respect to y-axis gives the negative side, the left-hand side. Okay, so what I will do now is to graph the positive side. So when x is at least 0, then absolute of x is equals to x. I hope you remember that. When x is positive, then absolute of x equals to x itself. Which means then when x is greater or equals to 0, fx will be 2 to the power of negative x. 2 to the power of negative x looks like this. Okay, but we will take only when x is 0 or positive. Okay, now let's put that into practice. So if I use the graphing paper now, then the graph will be as the following. This is the y-intercept, and then 1/2, 1/4, so on and so forth, right? Okay, looks like this. So that's for the right. It's supposed to, if I continue to the left, it's supposed to look like this. It's supposed to look like that. If I continue to the left. But we just need the positive branch, right? Okay, now then, once I get the positive branch, I will reflect that with respect to the y-axis. So when I do the reflection, I will get this guy, this guy, this guy, this guy. Okay, that's the graph of 2 to the negative absolute of x. Okay, that's the graph of 2 to the negative absolute of x, which actually we can write it this way. Fx equals to 2 to the negative absolute of x. That's the same to 2 to the negative x for x at least 0, and 2 to the negative of negative x for x negative. Okay, which if we simplify a bit, just for cosmetic purpose, but we still need to do that. The left-hand side basically the graph of 2 to the x, but only the negative portion. Okay, so if you see that from piecewise defined function, then the graph on the right-hand side is actually part of 2 to the negative x, but you only get the positive branch. Okay, and the graph on the left-hand side is actually part of 2 to the x, but we only take the negative branch. Okay. Now, so actually, if I use another function, so you can imagine what happens if I have fx equals to 2 to the absolute of x, which is actually question number 23. which is actually question number 23. Then you will see 2 to absolute of x later on will give you this portion. When x is positive, it will give you 2 to the x. When x is negative, then 2 to the absolute of x will give you 2 to the negative x portion on the left-hand side. Okay. The yellow one here, the yellow one, 2 to the power of negative absolute of x. Okay, so things that you can try to use, the tools that you can try to use is try to observe the symmetry of the functions. And this applies to actually all functions, not only for exponential functions, not only for polynomial, nor only for rational functions. No, for all functions. For all functions. Now then, another thing is if you deal with absolute value, try to see that from a piecewise defined function point of view. Okay, and now in this case, it happens that the symmetry already helps. Okay, and doing that reflection, piecewise defined function confirm our view. Now another one is two more, but I will not do these two questions in full. Number 26. Number 26, we have fx equals to 2 to the negative x plus 1 squared. Okay. Now, how do I do this? I will start with y equals to 2 to the negative x squared. Now, I don't know what the graph of that look like, but if I can graph that, then 2 to the negative of x plus 1 squared is actually move to the left, move left 2 units. I'm sorry, 1 unit. Move to the left 1 unit. Now then, Thomas, what is the reason you actually pay attention to this instead of attacking that problem right away? Well, because this function here has y-axis symmetry as well. Think about it. If you replace the x by negative x, okay, if you replace x by negative x, let me call that g. Let's call this gx here. Okay, so g negative x will be 2 to the power of negative x squared, but that's 2 to the negative x squared, right? So this graph here has y-axis symmetry. Now then, what do we do? After that, we move the whole graph to the left 1 unit. Okay. So here's what I will do. So what I will do is I'll do the table, okay, but for 2 to the negative x squared. So when x equals to 0, this is 2 to the 0, that's 1. When x equals to 1, this is 2 to the negative 1, that's 1/2. And this is 2 to the negative 4, that's 1/16. Oh, that's very small, right? Okay, so pictorially, let's say this is 0, 1, this is 1/1/2, this is 1/16. Actually, it dies down really fast, right? And then it's kind of, it looks straight, but it's not though. It's not straight. Okay, and then later on, I will reflect that. Okay. Now this will give me 2 to the negative x squared. Now then, from there, I will move this 1 unit to the left. Okay, I will move it 1 unit to the left, or another way to look at that is moving the y-axis to the right 1 unit. So the graph later on will look like approximately like this. if I move 1 unit to the left, this is -1, this is 1. This is 0, this is 1/2. If this is 1, this is 1/16, right? Okay, now the thing is, when you reflect with respect to x equals to -1, and the 0 will correspond to -2, the 1 will correspond to -3. Okay, imagine if you have x equals to -1 in between. So if you go 1 unit to the right, you get 0, 1 unit to the left is -2, then both of them should give you the same value. Then let's actually graph that. I will rescale it. Okay, I will rescale this. So this is, let's say, my 1 is here. Let's say this is 0, 1. I'm sorry, not 0, 1. I move it to the left. -1, 1. Let's say this is my -1. Oh, but it's not nice to. No, I cannot rescale it that much. Okay, let's say this is -1, 1. When x is 0, that's 1/2. When x is -2, that's 1/2. And then when x is 1, that's 1/16. So 1/2 divided by 8 is very small. It's very small. Like this. So the graph will be approximately like this. But it dies down real super fast. It dies down super fast. Okay. Yes, we have axis of symmetry at x equals to -1. Okay. So notice that even though we don't have, it's not symmetric to y-axis, I actually attack this graph. I attack this graph from the one before. I move it to the left 1 unit. I deal with this later. I see it this way first. Okay, I see it that way first. Okay, that's for number 26. Now, number 28 is another animal. We have fx equals to 3 to the x minus 3 to the negative x. Let's see what happens if I try f negative x. F negative x will be 3 to the negative x minus 3 to the negative of negative x. That's 3 to the negative x minus 3 to the x. But that is the opposite of 3 to the x minus 3 to the negative x. Therefore, we see that f negative x is equals to negative fx. That's an odd function. It has origin symmetry. So what I plan to do is I will sketch the graph on the positive side. Okay, I do plotting. I still do plotting. I sketch the graph on the positive sides, and then I reflect that with respect to origin. After that, this is 3 to the x, 3 to the negative x. So when x is 0, y is 1 minus 1, which is 0. When x equals to 1, I will get 3 minus 1/3. That's 2 2/3. When x equals to 2, I get 9 minus 1 9. That's 8 8 9. Okay. Let me use these 3 coordinates to help me to graph. Zero, 0, 1, 2 2/3. 2, 8 over 8 and 8, 9, almost 9. So it will look like this. It will look like this on the right hand side. Okay. But then you copy paste that thing, you reflect that the other way around. 6, 7, 8. If you copy the red one and then you rotate that with respect to the origin, it will look approximately this. Okay. You can confirm that this is actually an odd function. Let's see what happens if we see the graph using our graphing paper, our graphing software. Yeah, I want to know what it looks like too. Precisely, it looks like. We have 3 to the x minus 3 to the x. Okay, at least we can confirm that we have origin symmetry. Right? Yeah, we can confirm that we have origin symmetry. Imagine if you rotate this graph around that origin 180 degrees. You make it upside down and you will see exactly the same thing. Let me copy paste this so that I can say better things. Okay. That's what the graph. Now, what I meant by if you rotate 180 degrees is the following. If you rotate 180 degrees, okay, rotate 90 degrees, that's what it looks like. Rotate another 90 degrees, that's what it looks like. You see that? It's the same, right? That's after I rotate 180 degrees with respect to the origin. That's the order what we meant by origin symmetry. Okay. Now, but if I undo that, you see the same thing, right? Okay. Now, I hope that explains origin symmetry even more intuitively. Now, let's go on. Let's go on. More details here. What if you see the graph and you need to find out the equation? So, for example, they give you the graph number 32. They give you the graph number 32 where you see the y-intercept is 0, 5. You have another coordinate 1, 7. And then horizontal asymptote is y equals to 1. Now we need to find the equation. Fx equals to what? They call that b instead. Coefficient b times a to the x plus the constant. We want to find the a, the b, and the c. We want to find the a, the b, and the c. Now, you see that the horizontal asymptote, if I try to sketch that a bit, it looks like this. So the horizontal asymptote here is y equals to 1. Yeah, you can refer to your book, y equals to 1 here. This is 0, 5, and this is 1, 7. Okay? Now, you see that horizontal asymptote is 1, y equals to 1, right? So that will be your c right away. That will be your constant. X equals to b times a to the x plus 1. Now then, how do I get the b? How do I get the a? Well, let's do this first. When x equals to 0, the y is 5. Right? So the y is 5, the x is 0. But whatever the a to the 0 is 1. So b equals to 4. We update our equation now, so fx equals to 4a to the x plus 1. Then use another coordinate to help. 7 equals to 4 times a to the 1 plus 1. This is 6 equals to 4a. So the a is 3 halves. Okay, now we get the full equation. So fx equals to 4 times 3 over 2 to the x plus 1. Okay, now more things can be said about this exponential function, but let me just leave it here. Okay, let me just leave it here. Suggested homework from 4.1, 4.2 will be from number 1 to number you can try up to number 39. You can try up to number. By the way, exponential function is the type of function that being used a lot in science. So if you're in chemistry, biology, physics, of course math, you will see a lot of exponential functions. Okay. Now, let me go on to 4.3. Nothing, not a lot of things to say from 4.3 on itself, except that 4.3 natural exponential function. Natural exponential function. Let's define the number e. This is an irrational number, just like pi. That's an irrational number. In fact, they even call a transcendental number. The number e is an irrational number. Approximated is an irrational number. Approximated by E is approximated by 2.71828 if we round it to 5 decimal places. But you can use that approximation from calculator. Calculator will give you even more decimals. Now, how do we get that number? It comes from something to do with calculus, but you can try this already. It comes from this expression, 1 plus 1 over n to the n. 1 plus 1 over n to the n as n goes to infinity. As n goes to infinity, then when n is very, 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 very big, then it gets to e. Okay. Now our textbook actually show that number on page 275 for how they actually did it. And you can use Excel actually to do this. You can use Excel to do this, to get that number. You know what? Let me spend some time to show you how to use Excel. Excel is a program that I really expect every student from college level to have a middle level mastery level. Okay, a mid expertise. You don't need to be super good, but you need to know some Excel. Okay, now, of course, at this point, I expect you to know how to use Word already. Okay, for you to write papers, right? And Excel when you need to deal with spreadsheet. Okay, but let me spend some time. I wonder if I can have that here. Let's see. Okay, this is what Excel looks like. Okay, and then let's say we use 1, 2, 3, 4, and I make it 10, 100, 400, 1,000, 5,000, 10,000. When the end is 10,000, maybe 200,000, 1 million, and then 3 billion. Okay, and then for the formula, that's for the n. That's for the n. Now, what happened with that expression 1 plus 1 over n to the power of n? Okay, we want to compute that. Now, I use Excel to help me computing it super fast. That's 1 plus 1 over whatever number you have on the left-hand side to the power of whatever number you have on the left-hand side again. So when n equals to 1, that expression is 2. Now, the thing is, when we increase the n, it seems like the value is increasing. Right? Notice that? But then you may think that eventually it goes to infinity. It turns out that's not the case. That's not the case, because even though it is increasing, the increase slows down. Okay, now suppose I make it a super effing big number here. Make it 9,999,999,999,999,999. Okay, I think that's big enough. Oh, should not be a number. I don't want this to be. Oh, that's very big already. Okay, well then that's a very big number. Okay, and then let me copy this here. Why it looks like that? I'm not supposed to. It's not supposed to. Let me make it not too big first. The computer cannot handle it. I need to use equal sign of 1. Make that to be a number. Make it 400 billion. 1, 2, 3, 1, 2, 3. That's 400 billion. So this is equals to. You see, if even though the n is already 400 billion, the number doesn't change yet. Now, if I want to make it even more sensitive, I increase the number of zeros. So the number of decimal places. Okay, but it is consistent that it will be the first 5 decimal places is given. Okay, in fact, this is accurate to 8 decimal places. Okay, if you go on further, then it gets more sensitive. Okay, it doesn't stop there though. It doesn't. It is just that the number here, as you can see earlier, that the number I use is way too big. It's beyond the ability of my computer to handle, such that the accuracy here is also compromised once the number exceeds that number. Okay, but at least now we know that that E will be, for the first 9 decimal places, will be 2.718282. That's 6 decimal places. 053. That's 9 decimal places. Okay, now, don't worry about this though. I just show you an example how to use an Excel to do a simple computation for our approximation. Okay, let me turn that off. Now, that's what that E means. That's what that E means. So what happened with the exponential function? So fx equals to e to the x will have the same behavior similar to 2 to the x or 3 to the x. In fact, the graph will be between 2 to the x and 3 to the x. The y-intercept is 0, 1. The coordinate here is 1, e, and the coordinate here will be negative 1, 1 over e. Okay, now how to graph that? The graph will also done very similarly the way I graphed last time. The way I graphed last time will be very similar. Now the thing is, this E is being used a lot. This E is being used a lot. Now, let's do some problem from this section, the one, especially the one including the solving equation, because the e to x is a one-to-one function. How do we use this into solving equation? For example, number 12, easy one. Number 12, we have e to the 3x equals to e to the 2x minus 1. Yeah, you basically replace the e by some other variable, by some other base. It will still work the same way. So it has pretty much nothing to do with that e. But because the base are the same, we can use one-to-oneness. 3x equals to 2x minus 1. So x is negative 1. Mickey Mouse. Okay. Then using that idea, the one-to-oneness and the range to be positive to solve number 16, for example. Number 16, we have find the zeros. The zeros of fx equals to x negative x squared e to the negative x plus 2x e to the negative x. What I will do, I do factoring. I can factor x and e to the negative x out. I get negative x plus 2. Now, to find the zeros, then, to find the zeros, I will set this function equals to 0 and then solve it. Now, this function consists of 3 factors. So either x equals to 0 or e to the negative x equals 0 or negative x plus 2 equals to 0. Okay, so we get one solution here. Now the one here, we have no solution. No solution. Why? Because the range of e to the negative x is from 0 to infinity, but never 0. Right? Basically, e to the negative x will never be 0, whatever x you use. And then from the last part, x equals to 2. So there are 2 solutions here. And e to any power will never be 0, will never be negative. Okay. Now, once you get into more word problems, then you will see something called exponential growth. Exponential growth. Has something to do with the bacteria, for example, viruses, or population in general. Okay, let's say I do number, which one I would like to use? Number 21 and 22, is that what I want to use? Let me do number 24. Yeah, anything that follows exponential growth means AT, the amount at time t, is equals to A sub 0, the amount at the beginning of observation, times e to the kt. It will be growth when the k is positive. Okay, actually it will be dk, exponential dk, if the k is negative. Okay, that's the key. So every time you see exponential growth and exponential decay, have this in mind basically right away. To the point that you should have memorized this. You should memorize this. Okay, let's see. Suppose, for example, I pick number 24. Number 24. In 1985, population estimate of India, the population is 766 million. And then the population has been growing continuously at the rate of growth is 1.82% per year annually. Okay, so as the reference, if 1985 is the reference, then A sub 0 equals to 766. Okay, and then this rate of growth, 1.82% annually, will tell us the K equals to 0.0182. Okay, now assuming that this rapid growth rate continues, estimate the population in 2015. 2015 is a mere 30 years from 1985. So the t is 30. Okay, now the model from this tool give us the amount of people, or the textbook use n, in this case the number of people, equals to the initial in 1985 e to the 0.0182t. Okay, that's the formula. So what happened when 30 years later, A30 in 2015, and that's 30 years after 1985, that will be 766 million times e to the 0.0182 times 30. Okay, if we use calculator, how do we punch that? Now, I assume you have scientific calculator. The calculator I have here is not though. It's a graphing calculator. Now, let me show you how to use that. But you need to know how to use your scientific calculator. Okay. I have 766 times, now e to that power, I will use this one here, e to the x. Second, e to the x, okay, and 0.0182 times 30. And I will get 1322, what's that? 1322.37173 million. So it is estimated that by 2015, they will have 1,322 million people, if you round it to the nearest million, okay, or approximately 1.3 billion people there with this kind of growth rate. Even though every year it only grow by 1.8%, right? Okay, 1.8% more. So how to say that? So for every 100 people, in the next 1 year you will have extra 1.8% on average. With that kind of growth, if you continue for 30 years, you almost double the population. And using these, if you work for a government later on, especially in the planning, then you need to think ahead. Like, okay, 30 years later, we expect to have this number of people in our population. Then what happened to our infrastructure? Then of course we need to build more houses. We need to build more streets, right? More streets. We need to get prepared with our offices, the government offices, to support this bigger population. Okay. Now, with that said, then you know that you don't want to build your housing too close to each other, such that you cannot pave the street to connect them. Yeah. What you don't want to happen is, you build a crowded housing here, and you expect that to grow, but then the streets that goes through between these houses cannot expand because you already have houses there. You see? Okay. So the way I think America's doing that is they actually have quote unquote a new place. Okay. But they already have a blueprint in which later on the freeway will be here, so that you cannot build anything there. Freeway like that. Okay. Instead of like you just build anywhere you find an empty space. That will not do. Okay, that will not do. Of course, at the same time, if you live in, that's the good thing about America. I don't know about our other country though, but in America, the residential area is not the same with, they try to separate the business area and residential area. Why? What you don't want to happen is they take over our residential area and make it business. So it just take one or two very rich conglomerates to buy everything in my city, the residential neighborhood, and make it a business area. That kind of zoning is necessary to protect me from those kind of people. Of course, it will increase my land price, but increasing my land price also means if I sell my house, I will have harder time to buy another place, and that will be far from current house. Okay, I need to go even further to the east of LA to find a reasonable price house, but at the same time, it will be too far from the place I work. Okay, that's the positive thing about how America's been city planning being done. You know, it's like a lot of things put together, and doing this, put this together with your statistic, actually very helpful for you to see what can be done. Okay, that's for number 24. That's exponential growth. How about exponential decay? Let's see, number 28. Let's see number 28. The radioactive tracer, I think that's chromium. Yeah, I think that's chromium. Chromium 3051 can be used to locate the position of the placenta in a pregnant woman. Now, often the tracer must be ordered from a medical lab, and because of the decay and the number of units of the tracer present is given by this formula. The amount of tracer isotope in that uh, tracer is a t equals to a sub 0 e to the negative 0.0249 t. Now, because it is negative, we know it is decaying. Okay, it is decaying at the rate of we call that decay rate, 2.49% per unit of time. I think in this case is the number of days. T is in days. Okay, then part A. Okay, part A. They ship 35 units. They ship 35 units, and it takes 2 days for that thing to arrive. Now then, and how much tracer left by the time that units that tracer arrive. Okay, so that will be the a sub 0 is 35, e to the negative 0.0247249 times 2. Then you use your calculator. Use my calculator. I think, am I still here? Yeah. Use my calculator. So there will be 35 times e to the negative 0.0249 times 2. 33.29969. 33.29969. Suppose we reverse the question. 35 units needed. Okay, and again, it takes 2 days for the shipping to arrive. Now then, what is the minimum they need to ship from there? So what is the A naught? The question is, what is the A naught such that after it arrives, it's at least 35. Okay? Okay, so let's see. A2 should be at least 35. Okay, but A2 is A sub 0 e to the negative 0.0249 times 2. So if I use calculator for that, e to the negative 0.0249 times 2. What's that? That's 0.95142. 95142. 95142. A sub 0 is greater than 35. So A sub 0 will be 35 over that ugly number. Okay, so let's use this 35 divided by that answer will give me 36.78 something. That's at least 36.78713. Okay. So if I round it to the nearest 1 or 2 decimal places, then A sub 0 will be, you can use 36.7879 or even further 36.8 units. So that once it arrives, it still have at least 35 units. Okay, that's for this 4.3, your suggested homework from here. Not supposed to be a lot. Suggested homework from this 4.3 will be number 1, number 3, and then number 11 to maybe up to number 25 is good enough. Again, just do the odd ones. Okay, let's take a break. We come back in 10 minutes. And that will be 125. Okay, let's start again. I am about to start 4.4, but I don't think with the time I have, I can finish it. Your test 3, your test 2 will go up to 4.3 only. Your test 2 will go up to 4.3 only, 2.7, 3.1 to 3.6, and 4.1 to 4.3. Okay, now I really hope you will watch these lecture videos such that you know this update. Okay, because so far nobody attend my lecture, but I assume you watch my lecture video. Okay, now that's for the update for the test 3. Now the thing is, in my old test 2, in my previous test 2, sum includes I should not use S there. Sum include logarithmic, which is 4.4. Okay, sum sorry, I guess the signal was bad earlier. Okay, yes, let me update you again. I don't know where the connection was cut off. So our test 2 updated. I think yesterday I said that our test 2 up to 4.4, but because of the time, I don't think I can finish 4.4 in half an hour. So your test 2 will be up to 4.3 only. Now, the thing is, you need to pay attention to my previous test 2. Some of them include log, some of them not including log but include exponential, some of them not including exponential at all. Okay, so you may need to take a look on some problems instead of only one. Take a look on some test tools that what you don't want to happen is like you don't study the exponential one, the one with exponential function. Now let me bring you to my website to see which problems you can, which old tests that you can study from. Let me share this browser with you. Here, arjuna.com. Go to Thomas Arjuno, and then go to teaching, previous teaching. And then from that previous teaching, at SMC, of course, you can take a look on Spring 20. I don't know if I post anything there. Spring 20, Math 2, SMC. Yeah, I have up to test 2 there. Okay. Yeah, I have up to test 2 there. How about 419? 419, I have test 2. Let's take a look at the test 2 there. Test 2. I think this one, 419, does not include exponential. Yeah, but it went up to 4.1, no 4.2, 4.3. But I will for sure put 4.3 in this test for you. Okay. Now then, if you go back further, now Math 26, which is basically college algebra. Oops, I don't have that here. 417. Yeah, 417, 426. You can take a look on their test 2 also. Okay, in fact, their test 2, I believe, will have polynomial. Okay, and then if you look at their test 3, so college algebra, Math 26, right? College algebra is basically pre-calculus without trigonometry, without sequence series. So if you study from college algebra at SMC, you can actually look at their test 3 too, where they have rational functions. They even have the exponential functions. Okay, they have exponential functions and exponential equations, compositional functions, that's raw material, like inverse function. Okay, so I do recommend you to study from Math 26, Test 2 and Test 3. Math 26, Test 2 and Test 3. Let's see, Spring 17, recalculus, polynomial, rational functions, exponential function. They have log function. So in my Spring 17 Test 2, I have the log function, but you don't need to do that. The one exponential function you need to know. Okay, yeah, you need to know. So the log equation, you don't worry about that. At least not now. That will be in your test 3, but exponential function, exponential equation, the basic one, not this one. This one is actually not the, not the, this number 6 here requires you to know some log to do. That's why I will say that you don't need to know that equation. Okay, but the basic exponential equation you should know. The question number 8 here is actually a common question though. Okay, there's a common question, you need to know that. So again, I said this to emphasize that in my old test tool, some of them don't have log, some of them don't have exponential. The one that don't have log, don't worry, you still can study. But the one without exponential, you still can study, but make sure you get enough material from exponential functions and exponential equation, and you can get those from, of course, beside my old test, you also can see math, beside math 2, test 2. Okay, you can also see, math 26, test 2 and 3. Okay, that's about your test 2. Now let's go on with 4.4, which will not be in your test 2 but in your test 3. 4.4, logarithmic functions. Logarithmic functions. And again, this is not in test 2 but in test 3. Okay, let me start with a definition. For a positive and not 1, if we have log base a of b equals to c, that expression is the same to a to the c equals to b. Okay, now the one on the left hand side, we call that logarithmic form, log form. The one on the right hand side, we call it exponential form. Okay, now let's do some examples just to get used to this. For example, suppose, you know what, I take problems from the book. Number 2. The question is change to log form. Change to log form. Number 2a. 3 to the 5th equals to 243. Now that's exponential form. Then the log form will be log base 3. Now the 3 here is a subscript, so you will write it small and lower, of 243. Now that's 243 are regular size, equals to the exponent 5. Okay, the base, the argument, we call this the argument. The argument of log is the result of 3 to the 5th. I use color. I hope it can help you see the position and how they transform into log form. Now part B, 3 to the power of -4 equals to 1/81. Then the log form will be log base 3 of 1/81 equals to the exponent -4. Let me jump to part E. 3 to the negative 2x equals to P over F. I know that thing is ugly, P over X, right? But don't worry. The log form still looks similar. Base 3 of P over F. If the argument has fraction, this is what I mean the argument. If the argument has fractions, I use parentheses. Okay, I use parentheses. Equals to negative 2x. Now, how about if we change from exponential, from logarithmic form to exponential form? For example, number 4. Number 4, let's do part B. Log base 4 of 1 over 256 equals to negative 4. That's the log form. So what is the exponential form? There will be the base to the exponent equals to the argument. Okay, so this is the base. This is the exponent. This is the argument. Okay. Bring out your childhood pattern recognition method mode. Like if you have this color in form of logs, then what will that happen if you write it in exponential form? Okay, so see how the coloring actually changes. I hope that helps. I hope that helps. Okay, how about part D? Part D, log base 6 of 2x minus 1 equals to 3. So the exponential form will be the base to the exponent equals to the argument. Now, how to solve that, that's another story. Okay, we worried about that later. Now, with that transformation from log form to exponential form and then exponential form to log form, then we can do more questions from here. For example, number 6, solve for t. Number 6, we have 3a to the 4t equals to 10. Then how do we solve for t? How do we solve for t? I will divide by 3 first. That's 10 over 3. Okay. And then the base is a, right? So I change it into log form. Log base a of 10 over 3 equals to the exponent for t. Then from there we divide by 4. So t equals to 1/4 log base a of 10 over 3. Okay. Let's see, how about number 10? Ooh, that looks so nasty, but you will need to know how to undo order operations. Okay, solve for t again. So for t, L equals to m a to the t over n minus p. Now I need to solve for t. So I will add p first. Oh, do I have a negative there? No, I don't have it. Okay, good. And then divide by m. So that's a to the t over n. Right? Then now I change into log form. Log base a of the argument, which is the answer there, equals to the exponent. Then multiply by n. So n times log base a of L plus P over n equals to t. Okay. Today I think I will not go into graphing yet. I will focus on graphing tomorrow. Today we focus on changing into log form, changing into exponential form, and computing basic numbers. Okay, you will see from our textbook, number 11, 12, 13, 14, basically changing into log form, into exponential form. Now, some notes before I forget. Notes. Now, if you see log without base, if you see log without base of x, this actually means log base 10 of x. We call that common log. Okay, if you see log without any base, then it is base 10. Okay, now on the other hand, if you see natural log ln x, that is actually log base e x. We call that natural log. Okay, but with this note, with this sake for this note, I have something quite terrible to tell you. When reading from older books or older journals, older articles, like a lot older, like I'm talking about like 30 years maybe or 40 years maybe, though, and including if you deal with older professor, okay, be careful, be careful with those notations. Some used log x, which is supposed to be base 10, to be natural log of x. Now, how do we know if their log is natural log? We know it if they write log base 10 of x. If they use the base 10 for base 10, if they actually write the 10 for base 10, then if they don't use that base 10, it is natural log. Okay, if they actually write this notation in that book, it means if they don't write the base 10, it refers to natural log. Okay, now actually the best way is ask the teacher, or when you read the book, know that there is possible difference in definition. Okay, so basically in old time, when they write log, in old time, they don't recognize natural log yet. So at that time, they don't use this. Okay, so they use log x for natural log, but for base 10, they still write the base 10. That's what happened at that time. Now, but in more recent literature, if in more recent literature, we will use this. Okay, and that's what I will use also. Our textbook actually follow this newer tradition. Okay, that's one. Actually, there's another thing that I forgot to mention earlier, is this. Why does the base can't be 1, can't be 0, can't be negative? Okay, let me tackle it one by one. From exponential point of view, okay, why can't, if the a equals to 1, then my exponential function fx equals to 1 to the x, but 1 to the x is just 1. For any x, 1 to that power will be 1. Now, fx equals to 1 is no fun. Why? It's actually just horizontal line, right? Okay. Now, the thing is, not only that it is not fun, for a reason that it is then not a one-to-one function. Remember that exponential function is supposed to be one-to-one, right? Either strictly increasing or strictly decreasing. Okay. And when you have x, when the base is 1, suddenly it is not increasing, it is not decreasing, therefore it is not one-to-one. So they kind of like kick this base 1 away. They say, no, we don't want this. Why? Because you don't really fit what we commonly have. Okay, so yes, this exponential function discriminate against base y equals to against base a equals to 1. Now, what happens if a equals to 0? Now, fx 0 to the x is, yes, almost right, but not really. You say 0 to the x is 0, right? But that's actually not true. 0 to the x will be 0 only when the x is positive. Okay, it will be undefined for x is 0 or negative. In other words, 0 to the 0 is not 0. 0 to the 0 is not 0. Okay, 0 to the 0 is not 0. 0 to the negative 2, for example, that's actually undefined. Well, because 0 to the negative 2 means 1 over 0 squared. Okay, so if the exponent is negative, it's undefined. Now, what happens if you have 0 to the 0? 0 to the 0 have the meaning of 0 over 0. It's not 1, it's not 0, it's undefined. Okay, 0 to the 0 is undefined. So the graph, if we graph this, the graph of 0 to the x, we see that if we look at the graph, it is also not fun because it looks like this. It's undefined on the negative and 0, and then suddenly it is well defined on the positive side. So this is what the graph looks like. This is what the graph looks like. Okay, it's still not increasing. Okay, it is still not increasing, not decreasing, and it's actually worse than when the base is 1. It's not, the domain is not all real number. Okay, the domain is not all real number. Now, the last part, what happens if the base is negative? Then we may have some ambiguity. We may have some ambiguity. It has something to do with what we call well-definedness. Like, for example, if I use the base to be, what is good? If I use the base to be 16, negative 16. Let's say a equals to negative 16. Then what is negative 16 to the power of 1/2? What is negative 16 to the power of 1/2? Negative 16 to the power of 1/2 is the same to the square root of negative 16. We know this is 4i, but therefore it is not a real number. Okay, that's not a real number. However, at the same time, you know 1/2 is equals to 2/4, right? 1/2 is equals to 2/4. So negative 16 to the power of 2/4 is the 4th root of negative 16 squared. But that's the 4th root of 256, which is 4. That's a real number. Now, what's wrong with this? What's wrong with this? So you say, let's say the base is negative 16. So f1/2, right? So fx equals to negative 16 to the x, okay? So f1/2 is negative 16 to the power of 1/2. That's not a real number. However, f2/4 is a real number. Maybe I write this way here. So which one is the true one? Which one is the true one? Is it a real number or not? And the answer is, to be more precise, cannot be said. Why? Because 1/2, the power of 1/2, is supposed to be the same to the power of 2/4, right? I mean, 1/2 and 2/4 are the same number. But when you plug that in under the to the exponent of base negative 16, you come up with two different results. One of them not real number, the other one real number. Now, because of this possible ambiguity, then we decided not to talk about negative base to start with. Okay. That's the reason we don't want to include this negative base. Okay. Now, I hope then with this said, then I explain why we don't want the base to be 1, why we don't want the base to be 0, and why we don't want the base to be negative. Okay. In the last 4 minutes, let me do more examples, but this time to compute some log. Compute some easy log. Now that's for foundation for tomorrow. For example, number 16, part A. Log base 8 equals to what? Log base 8 of 1 equals to what? Okay, eventually you need to memorize this, but let's call that x for now, and we will solve for x. Okay, we will solve for x. Now, but the way we solve for x is we change this bit back to exponential form. A to the x equals to 1. But we know 1 can be written as 8 to the 0. Therefore, by 1-to-1ness, x equals to 0. So, log base 8 of 1 is 0. In fact, in general, log base anything of 1 is 0. Part B. Log base 9 of 9 equals to what? Suppose I don't know, let's call that x for now. So in exponential form, 9 to the x equals to 9, which we can write as 9 to the 1. So therefore, by one-to-oneness, x equals to 1, and log base 9 of 9 is equal to 1. So in general, log base a of a equals to 1. Part D. Now you can try to do part C if you like, but you will see it's not possible. Log base 6 of 6 to the 7 is what? Again, let's call that x. You see my trick here? I basically rewrite that into exponential form. 6 to the x equals to 6 to the 7. So by one-to-oneness, x equals to 7. So log base 6 of 6 to the 7 is 7. In general, log base a of a to the n equals to 10. Part D. Oh, actually, part E. Last one. And I will continue tomorrow. 5 to the log base 5 of 4 equals what? Let's call that x. And we will see this as exponential form. This is the base. This is the exponent. And this is the answer. Okay? Then if we see that exponential form, then log base 5 of x, I change it into log form, is equal to log base 5 of 4. Now tomorrow we will see, once we do the graphing, that we will be more convinced that log is the inverse of exponential function, and therefore it also carries the one-to-oneness. But log blah equals log blah means blah equals blah. Okay, so log base 5, 5 to the log base 5 of 4 is equals to 4. In general, a to the log base a of x equals to x. Okay. Now I would like you to do some problems from number 1 to number 19. Number 1, so suggested homework from this 4.4 or the 4.48, number 1 to number 19 to the odd ones. Again, this 4.4 will not be part of your test 2. It will be part of your test 3. Okay, see you then tomorrow.